Hey everyone, this lecture is going to be on nuclear fission and nuclear fusion. So we have our objective sheet copied over here, and I've already highlighted from the objectives in yellow the ones that you should feel comfortable with from when our SL students taught you guys about nuclear and atomic basics. Today, this lecture is really going to zoom in on identifying fission and fusion reactions. This falls under Objective 3, can solve problems related to nuclear reactions. So we're really going to lay the basis of what fission is, what fusion is. We'll do a little reviewing, and then from here we're going to build. So as a warm-up, I would like you to think back to your July break assignment from Unit 7 on energy production. You already know some things about nuclear fission and nuclear fusion from that energy production unit. And so I want you to pause the video here, and I want you to brainstorm everything that you remember about fission and fusion, anything about nuclear energy. Okay, so I want to highlight some really important things that came out of the Unit 7 energy production, just as a refresher for you. The first thing to remember is what exactly is fission and fusion. When you hear nuclear fission, you should think that atoms are splitting apart. So you take a big atom and it is splitting into smaller atoms. When you hear nuclear fusion, this is when atoms are coming together. They are quite literally fusing together. So you have smaller atoms and they're fusing to make a large atom. Now, our power plants, when we say we have a nuclear power plant, our power plants are using nuclear fission. You may be wondering, why can't our power plants use nuclear fusion? Well, in order to have something fuse, undergo nuclear fusion, you need really high temperatures and high pressure, like comparable to the sun. And we actually can achieve this in labs, but it takes a lot of energy in order to achieve these conditions. And in the end, it takes more energy to create a nuclear fusion power plant than it would compared to how much it's actually producing. So yes, we could create a nuclear fusion power plant, but man, it costs so much energy that we're really not going to get usable energy out more than what we put in. So it's just not really practical right now. Let's take a closer look at what a power plant for nuclear fission actually looks like. You might remember some of this vocabulary. Things like fuel rods, the reactor core, the moderator, a chain reaction, control rods, or the heat exchanger. These are some important vocabulary words around nuclear power plants that you really want to be familiar with. Let's talk through the energy transformations. So in the core, in the reactor core right over here, we are going to start with nuclear energy, meaning that we have an atom that is unstable. It is essentially stored up energy, and it really wants to become more stable. So it is going to undergo nuclear fission and is going to release that energy. Now, when that energy is released, it causes particles, mainly neutrons, to go faster, to get some kinetic energy. And that's really what's happening right in here in the steam part. It's causing those particles to move faster and faster and faster, warming up. Now that warming up is really then thermal energy, and that thermal energy from the steam goes through the steam line and hits a turbine. The steam causes the turbine to start rotating. The turbine gains kinetic energy of rotation, and that turbine then turns a generator where you can generate electrical energy. And after all, that's what we want from our power plant. We want that electrical energy output. Now let's go back to the very beginning, inside of our reactor and that nuclear energy. Let's talk about the fuel. The fuel for nuclear fission is called uranium-235, or also known as enriched uranium. Naturally occurring uranium is sometimes uranium-235, but more commonly uranium-238, uranium-234. There's isotopes of uranium. And the uranium that we have found to be most effective in nuclear fission is uranium-235. So there's an enrichment process in which you take the naturally occurring uranium-238, 234, and you make it into enriched uranium, uranium-235. A reminder of some of the advantages and disadvantages of nuclear fission. This comes when you compare nuclear power to solar or water or fossil fuels. So some of the advantages is that it's very environmentally friendly. It does not emit greenhouse gases, although we should consider and be realistic about the transportation of uranium, and that could contribute to climate change. We have a lot of nuclear fuel, a lot of uranium-235, and so we're not very concerned about running out anytime soon. A nuclear power plant is always on, and we use those control rods to produce exactly the amount of energy that we want over time. And so we have a good amount of control over this process. Last but not least, it's pretty cheap energy. Now, granted, constructing a power plant isn't super cheap, but once it's constructed, nuclear energy is pretty cheap. Some disadvantages, though, include the fact that, well, although we have a lot of nuclear fuel, it is technically non-renewable, which means eventually we will run out, but honestly, we have a long time before that happens. One of the biggest drawbacks, though, is that it creates nuclear waste that is radioactive and can be difficult to store safely. And along those lines, it's also a big concern to make sure that you don't have a nuclear meltdown in which that radiation can get to the public and be very harmful. In fact, in this unit, we're going to take a deeper dive into what exactly radiation is and what types are harmful and how. So this is where we are so far in our understanding of nuclear power. If any of this sounds unfamiliar to you, I would recommend pausing and watching this video. This is Mr. Maisley's nuclear power video. In fact, you watched it as part of that July assignment. So if you need a refresher, I recommend that video. Okay, so let's dive a little bit deeper. Let's first talk about nuclear fission. What is nuclear fission? Again, this is the splitting of a nucleus into smaller pieces. This is what we use in nuclear power plants. How exactly does this reaction work? How does it start? Well, the nucleus shown here, uranium-235, our enriched uranium. The uranium nucleus is going to absorb a slow-moving neutron. We often use the word capture here to think about that slow-moving neutron is kind of moving around inside of our nuclear reactor. When it's captured by this nucleus, it makes that nucleus highly unstable. When something's unstable in nature, it wants to get back to its stable position. And so what happens is it splits apart in order to make more stable nuclei. One common reaction is for our uranium to split into barium and krypton. And notice that 3 neutrons came out of this reaction too. You could imagine that these neutrons then went on to hit maybe another uranium nucleus and cause another nuclear fission reaction. And if you can get enough of those reactions, it can actually sustain itself and you can get a chain reaction. I want to explore that a little bit further, so I am going to go to this PhET simulation and show you around. This is a great simulation for you to play with as well. Okay, so here we are in the simulation. I'm on the Fission 1 nucleus tab, so we can look at just one fission reaction in more or less real time. So here's my uranium-235, my enriched uranium nucleus, and I am going to fire a neutron at it. So let's take a closer look at what exactly just happened. So I'm going to fire the neutron at it, and you're going to see that that uranium-235 becomes uranium-236. It starts to wiggle around, and down here you can see it's not stable, it's not stable. So it undergoes nuclear fission in order to become stable. Now, after it undergoes nuclear fission, you're going to see 2 daughter nuclei, there they are, and 3 neutrons fly out. That's a very common reaction. Of course, nuclear fission is going to be splitting, so we expect there to be daughter nuclei, and those neutrons will go on to help create a chain reaction. I'm going to switch over to the chain reaction tab, and I'm going to add a bunch of uranium-235. I'm again going to fire just 1 neutron, a slow-moving neutron, in order to get it started. And you can see that the neutrons from other reactions start to be the slow-moving neutron to create a new reaction. And it's still going. Now, you can change this up. The more uranium-235, the more enriched uranium. You can see that that reaction goes a lot faster. You can also introduce uranium-238 to see how that plays in. So this is a mixture of uranium-235 and uranium-238. Let's try to get just about even amounts. Ooh, as you can see, my first neutron that I fired hit a uranium-238, so it made uranium-239, which honestly is not that unstable, so we didn't get nuclear fission. So I'm going to shoot it again. That time it hit a uranium-235. And we got a couple more reactions from those neutrons flying out. But because there's so much uranium-238 in here, and uranium-238 is non-reactive or does not undergo nuclear fission as easily, we're really not getting that full chain reaction. So that's why we will enrich our uranium to reduce the amount of 238 and increase the amount of 235 so that we can get a reaction that can be a chain reaction, can be self-sustaining. There's some other features in this simulation that you can play around with. For example, a containment vessel over here. You can see what that does by putting it inside of something so the neutrons can't escape. Some interesting things to play around. I'll let you play. And also in the simulation is a nuclear reactor tab, which is pretty cool. We have a bunch of enriched uranium inside, but we also have control rods. And you can put those control rods out or in just like you would in a nuclear power plant. And in a nuclear power plant, you can see the power output, the energy produced. It looks something like this. So notice my control rods are all the way in. So what happens in one of these little columns kind of stays in that column. We're getting that nice reaction within the column. But if I start to remove these control rods, if I allow some of the neutrons from this column to be able to activate or cause reactions in the other columns, notice how I'm getting a more sustained and higher power output, higher energy produced. We even have a little thermometer here to help us track that energy. Because remember, this is going to turn into thermal energy, those little particles going faster and faster, eventually heating steam, and then that steam turning the turbine. Turbine connected to a generator to produce usable energy. Again, I really suggest going to the simulation and playing around a bit. It's a really excellent simulation of nuclear fission. So let's take a look at a few of these fission reaction examples. Notice that all of these fission reactions are starting with enriched uranium-235 and 1 slow-moving neutron that has been captured. So the beginning of these reactions are all the same. But notice that sometimes it goes into barium and krypton. Other times you get iodine. Other times you get different isotopes of barium and krypton. And really, it's just a probability which one you're going to get. There really is not a good way to predict, like, I want that one, so I'm going to make that one. Or I think this one's going to happen next. It really is a probability which of those functions you're going to, or which of those reactions you're going to get. A really important thing to notice in these equations, just as our SL students have taught you, is that we are seeing conservation of mass and conservation of charge. Our conservation of charge really comes by looking at the bottom number, the atomic number, and tracking the number of protons. After all, protons have a +1 charge, and so all of our bottom numbers should add up to be the same on the left and the right of the reaction. And of course, conservation of mass, we're really looking at the top number. The top number is our mass number, and that's the number of protons and neutrons. Notice that we ignore electrons when we talk about mass because electrons in comparison are so small that their mass is insignificant. So again, you can check that these equations are all good to go by checking both the top mass number, protons and neutrons, that's conserved as a way of showing conservation of mass, and checking the bottom, the atomic number, to show conservation of charge, checking the number of protons. And next up we have nuclear fusion. This is where two nuclei are joining together to form a larger nucleus. They are quite literally fusing together. Okay? In order to start nuclear fusion, you need really high temperatures. You need really high pressure, comparable to the temperature and pressure of the sun. Here is a nuclear fusion reaction. We have two nuclei coming in. They undergo fusion and you get a larger nucleus out. You also tend to get a neutron. Now you might be wondering to yourself, like, what is deuterium? What is tritium? These are fancy ways of really saying hydrogen. Deuterium is hydrogen 2, the isotope of hydrogen with 2 neutrons. And tritium is hydrogen 3, the isotope of hydrogen with 3 neutrons. Some common fusion reactions all start pretty similar. You see a lot of hydrogens and heliums running around. But if you notice, the products are always going to be bigger than your reactants. This is a key trait of fusion, right? Two nuclei are coming together, joining together, fusing together to make a bigger one. We still see conservation of mass. We see that by looking at the mass number, the top number, the number of protons, and the number of neutrons. We also see conservation of charge. We see that by tracking the number of protons in the atomic number on the bottom. So, let's finish up with a gear up problem. This gear up problem has a few parts to it. Pause the video here and try your best to do these gear up problems. Okay, let's take a look at our gear up problem answers. Question number 1 said, here's an equation. What could be a product? There are several answers here. I chose my answer as helium, 4,2. And I chose that simply because I can see that on the left side, my top number, my mass number, 2 plus 2, must equal 4. And so the right side, I chose 4. And then on the left side, my atomic number, 1 plus 1, equals 2, so my right side must have equaled 2. And the easiest answer for me to come up with was 4,2 is helium. Number 2, trying to identify X, an unknown. Really what you're doing here is making sure that mass is conserved by looking at those top mass numbers, protons and neutrons. Making sure that mass on the left and mass on the right is conserved. As well as charge. Charge looking at the bottom number, which is your atomic number, which is the number of protons. Making sure that the number of protons on the left and the right side is conserved. I want to show you here where you have a coefficient. This coefficient essentially distributes to both of those numbers inside. So this is kind of like saying 3, 0 as our mass number and atomic number, representing 3 neutrons, which have a mass number of total of 3, and 3 neutrons, meaning 0 protons. So from this, I could start to infer that X would need to have an 81 on the top and a 32 on the bottom. So I came on over to my periodic table and I looked for the element that had 32 as its atomic number. That element is germanium, Ge, with an atomic number 32. And that is how I determined that X must be germanium 8132. Question 3 is very similar, again applying the conservation of mass and conservation of charge, looking for that unknown. Remember that 2 coefficient gets distributed. And we can see that what's missing is a 144 on top and a 55 on the bottom. Coming over to my periodic table and looking for an element whose atomic number is 55, I can see that cesium has an atomic number of 55, Cs for cesium. So that tells me that the blank here must be cesium 144, 55. And finally, we finish up with question number 4. We are given equations that are already balanced, already showing conservation of mass and charge. We are asked if each equation is fission or fusion. So really the question here, are my nuclei splitting? Or are my nuclei joining together? The first one here, we start with 2 hydrogens, and it ends up being combined into a much larger hydrogen, as well as a proton. This would be an example of fusion. Remember, when you see hydrogens and heliums, it's kind of already a tip-off that it's probably going to be fusion. My next one here, we have uranium and a neutron combining to form beryllium, krypton, and 3 neutrons. This would be an example of fission. Our big uranium guy here is splitting into beryllium and krypton. Again, when you see uranium, especially uranium-235, enriched uranium, you're probably already thinking fission. The next one, again, is uranium. This time it is splitting into xenon and strontium. This is another example of fission. Notice here we are again, we have a couple examples of how the same reactants can split differently, and it's just probability which one happens. And last but not least, we have 2 heliums here combining to form a bigger helium as well as a hydrogen. This is an example of fusion. So, in this lecture, we really focused on how to identify fission and fusion reactions. We're also pulling on that yellow, highlighting that basic knowledge that we gained from our SL students. We started by looking at our prior knowledge that we learned in Unit 7 for energy production, trying to remember back to what nuclear power plants, nuclear fission power plants look like and how they function. Again, you have a refresher in Mr. Maisley's nuclear power video if you feel like you need it. We talked about fission, where the nucleus is splitting apart. It captures a slow-moving neutron, becomes highly unstable, and splits. It's really a way of becoming more stable in the products. We saw some reactions of fission, some examples that really probability determines which one will happen. But we do know in all of those examples, conservation of mass and conservation of charge must hold true. And we talked about nuclear fusion, when two nuclei join together to form something larger, often with hydrogens and heliums running around. And we looked at a few examples here, again seeing the conservation of mass, conservation of charge, but here forming that bigger molecule in the end, coming together. That's all for this lecture. Give the homework a try.